A titration is a special lab technique where we can find out the concentration of an unknown solution using a known solution. Typically, we do this with acids and bases, but there's lots of different reactions that we can determine with a titration. We add the known solution to the unknown solution until we reach the stoichiometric ratio. So what that means is we're going to add one of the compounds until the reaction is just complete. And that's what we call a titration. Once we reach that point that is where the reaction is complete, that is what we call the equivalence point. Our reactants are in their stoichiometric ratio, and we can determine the concentration of our unknown. We use a special piece of glassware called a burette, long, thin piece of glass that has very precise markings, and it allows us to measure multiple different volumes. The unique thing about a burette is the top is marked as 0 milliliters, and the bottom, there's different burettes, but typically 50 milliliters is pretty common. And so this is different than most glassware, because most glassware 0 is at the bottom and 50 or your other volumes are at the top. You read from the bottom up. This one you read from the top down. And so you're going to start your titration somewhere near the top. You record that volume. You dispense a certain amount of liquid going down the burette, and then you read that volume once you've reached your equivalence point. And to find the volume added, it's the final volume minus the initial volume. So typically our unknown solution will be put into an Erlenmeyer flask, and this is called the analyte. And the known solution typically is put into the burette, and this is our titrant. We do also add for acid-base reactions, we add something called an indicator. The indicator is a special chemical that signals the equivalence point. So in an acid-base reaction, it typically changes color right at the equivalence point of our chemical reaction. So the indicator that we typically use is phenolphthalein, and phenolphthalein changes from a clear, colorless solution to a pink solution at the equivalence point. The titrant in this case, because it is in the burette, it is the base. We add the titrant to the flask. As it gets added, the base reacts with the acid, forming new water molecules. In our middle example, we are not to completion yet because there is still acid that is unreacted. You'll notice that there is a faint pink color that is forming, but if the flask is swirled, it will go away. So very locally the reaction is complete where our water molecules are formed, but in the entire flask it is not complete. So upon swirling, that light pink color will disappear. Once we have reached the end point, we've added just enough base to completely react with the acid. the indicator is going to change color to a very faint pink color. It is easy to add too much base and turn it a deep fuchsia color, but we are looking for a light pink color that persists for about 30 seconds. Once you see that, you know that your reaction is complete. So let's try an example. So we're going to do a titration of 10 milliliters of hydrochloric acid solution that we don't know what its concentration is. We're going to add 12.54 milliliters of 0.1 molar sodium hydroxide to reach the endpoint. We want to figure out the concentration of the HCl. This is just like solution stoichiometry we've done before. So we can take and start with the solution we have the most information about. We are also going to have to know our chemical reaction so that we know what our stoichiometry is. So our HCl plus sodium hydroxide. To predict our products, we take the cation of one, combine it with the anion of the other. H plus and OH minus gives us water. Take the sodium, combine it with the chloride, and we get NaCl. If we look to balance this reaction, 1 sodium we're good, 1 chlorine, 2 hydrogen, 1 from the H plus, 1 from the OH minus, and 1 oxygen. So we are balanced. This is a 1-to-1 reaction. 1 mole of HCl reacts with 1 mole of sodium hydroxide. We're going to start with the solution we know the most about. 12.54 milliliters of sodium hydroxide. And there's multiple ways we can solve this problem. We can solve it as millimoles, we can solve it as moles, whichever you prefer. I'm going to convert it to moles. Now that I've converted the milliliters to liters, we can use our molarity of the sodium hydroxide to convert to moles. So 1 liter of solution is 0.100 moles of sodium hydroxide. Remember that capital M is moles over liters. Now that I'm in moles of sodium hydroxide, I can compare it using my balanced chemical reaction. So 1 mole of sodium hydroxide reacts with 1 mole of HCl from our coefficients. I'm going to stop there and calculate the number of moles of HCl. Which would be 1.254 times 10 to the negative 3 moles of HCl. Now if I want to find molarity, I need moles over liters. So I'm going to take my 10 milliliters of HCl and convert it to liters. And now to find molarity, I can take my moles of HCl, divide by the liters of HCl to find the molarity. Now there is a shortcut that you can take if the reaction is 1-to-1. So if the reaction is 1-to-1, you can use M1V1 equals M2V2. Acid goes on one side, base goes on the other. And the reason we can use this is because the moles are equal. So only 1-to-1 reactions. You can plug in the volume of your acid. We know the molarity of the base. We can divide by the 10 milliliters to get it on the other side. And we end up with the same answer.